Okay, welcome. In this video, I'm going to try my best to help you feel comfortable about working the problem set that's titled Bond Energies and Estimating Enthalpies of Reaction. Okay, so in this problem set, let's see if I can dial it up here. You start with methane, and what you're going to need to do is first, you're given a little description here. It says, okay, methane is burned in a combustion reaction. And you guys know what a combustion reaction is, right? So you know it's going to react with oxygen to form carbon dioxide and water. And then part A is I want you to translate that into a balanced chemical equation. Okay, so you know what the reaction is. Uh, you know, wrestle that into a balanced chemical equation. Then I'm going to have you illustrate the reaction using symbols, like models, and we've done a little bit of that, but I'll demonstrate that here in a little bit. And then we're going to use this table to sort of guide us through the process of coming up with an estimated enthalpy of reaction, and it's really cool. By using a table like this, a table of bond energies or bond enthalpies, we can take most reactions and we can come up with a very good estimate as to how much heat is going to be released or absorbed during the during the process of the reaction. So we're going to get to all that. Here, let me get myself organized here. Okay, so first, one little preliminary, and that is the following. We have to understand what the energetics are of bond breakage and bond formation. So, for example, let's take the simplest bond breakage there is. Let's say we have hydrogen gas, okay, and let's look at the process where we break the bond between the two hydrogen atoms to get two atoms of hydrogen. All right. Now, what does that actually look like? So, if you kind of visualize a single molecule of hydrogen gas, it's diatomic, and so it's composed of two atoms that are bonded together with a single covalent bond. And if we want to end up with two independent atoms, by breaking this apart, then we're going to have to, bust some heads, right? We're going to have to break the bond. And as you can imagine, these hydrogens, they don't like to hang out for just no reason. They're more stable when they're bonded together. And so things that tend to be more stable, if you want to drive them in the direction, of less stable, then you're going to have to put energy into the system. Okay, and so in terms of chemical potential energy, like we've talked about in class, if you break a bond, it's like doing this, okay, where the intact diatomic molecule is at lower energy, and then these two independent individual hydrogen atoms are at a higher energy. And if we can actually look up how much energy it would take to break that bond. So if you look at now this is where I want you to check your notebook and make sure that you have this handout. Okay, you've got to have this table of bond energies in order to do these exercises. So if we look up hydrogen single bond, we can see that the bond energy is 436, and the units for that you find up here, kilojoules per mole. So I don't want you to misunderstand. If you want to break the bond in one molecule of hydrogen, it doesn't take 436 kilojoules. It would take much less than that for one molecule. What this number means is it's per mole. So if you had 1 mole, that is, if you had 6.02 times 10 to the 23rd molecules of hydrogen, and you were going to break every single one of those bonds, then it would take 436 kilojoules. Okay, so this is on a per mole basis. I just want to be clear about that. So, to kind of finish off our potential energy diagram, now that we know the energy from the table, this is what this means. If you want to take 1 mole of hydrogen molecules and break those bonds, you're going to be going uphill, right? Now, conversely, what about the other way? Let's say you want to take 2 atoms of hydrogen and let them form a molecule, all right? So conceptually, that's like taking 2 individual atoms and you just put them together so that they can form their single bond again. And in terms of chemical energy, potential energy, that is an exothermic process, and the energy associated with that is now negative 436 kilojoules. And I should say per mole here to be precise. Okay. So now the last thing I'm going to say before we dig in here is, what color should I use? How about blue? All right. Bond breaking is an inherently endothermic process because you have to put energy into it. It doesn't happen for free. You got to work at it. Whereas bond formation is an exothermic process. Okay? So again, bond breaking is an inherently endothermic process. Bond formation is exothermic. All right, so it's very important that we remember that. Okay, so now let's go to an actual problem and see how do we apply that thinking. All right, so it says propane is burned in a combustion reaction. Okay, so we got to come up with a balanced chemical reaction for this. All right, so let's do it. Propane is C3H8, and we know that if it's combustion, it's going to be reacting with molecular oxygen to form carbon dioxide and water. Okay, now you need to balance this, and this one is pretty easy, and I think we did this in class not too long ago. So you got 3 carbons over here, so you got to put a 3 there. You've got 8 hydrogens, so you got to put a 4 here. Now we have, let's look at the oxygens. We've got 3 times 2 is 6 plus 4, so that's 10 oxygens on the right. So in order to get 10 oxygens on the left, we got to put a big old 5 there. Now we know the stoichiometry of this chemical reaction. So we've got A. Now part B, illustrate the balanced chemical reaction using a model diagram. Okay, all right, no problem. So we have 1 molecule of propane, and that's all. So now if you don't know the molecular structure of propane, I mean, we've talked about it a fair amount this year. It should kind of be in your head, but you can always just look it up. Just do a Google search or whatever, and you'll find it. All right, so that's propane, 3-carbon chain, with hydrogens filling in the rest of the valences. 5 oxygen molecules. Now, here it is important when we're doing thermochemistry, you have to know that there's a double bond between the 2 oxygens. It's not a single bond and it's not a triple bond. It's a double bond, and this is quite important, and I'll show you why in a minute. Whoops. Okay, so I got to do 5 oxygen molecules, okay, and then I'm going to draw 3 carbon dioxide molecules. And again, you need to know that the carbon atoms are double bonded to the oxygens in carbon dioxide, okay, and then we have 4 waters. And from our work on molecular geometry earlier this year, we know that they are not linear, they are bent with a bond angle of about 105 degrees. Okay, all right, so I'm doing this a little bit fast, and I'm sorry for my artwork. Okay, now I'm going to scroll down. We're going to lose the structure here for a second, but I just want you to know this is what I mean by if you're asked to illustrate a balanced chemical reaction using a model diagram, this is the kind of thing that you need to know. What this tells you is the type of molecules, the type of bonds that are connecting them, and how many of each different compound we have, right? So visually we can see that we have 5 oxygen molecules. Let me neaten this up. This looks like a triple bond almost. Okay. So visually you can see we have 5 molecules of oxygen and they are held together with double bonds and so on. Okay, so we're going to refer to this illustration in a minute. Let's see. Let me see if I can make some space here. All right, maybe not. Now, the table in part C, this is where we're going to take inventory of what we have. So we're going to go down all the bond types, and we're going to just tally up what we know. All right. So let's just start. So on the left side, we're going to write down what we know about bond breakage. Okay, and I'm putting a little reminder in here that breaking bonds is endothermic, and it's associated with a positive sign on the energy. So let's take a look at the bonds that are breaking first. All right, so let me go to green. So it looks like we have a few carbon-carbon single bonds. All right, so let's just make a little tally here. Carbon-carbon single bonds, and I see 2 of them. So we've got 2 of those. And then the rest of the bonds in propane are carbon-hydrogen single bonds, and we have 8 of those. So that's 8. And then we have 5 oxygen-oxygen double bonds, so we have 5 of those. And over here on the product side, it looks like we've got a bunch of carbon-oxygen double bonds. We've got 6 of those. And then finally, we've got a bunch of oxygen-hydrogen single bonds. And it looks like we have 2 apiece. So 2 of these bonds per molecule, but we have 4 molecules. So that's 4 times 2, that's 8. Okay, so now we're in a position to go to this bond energy table and look up the bond energies for each of the bond types that we just listed. So we know that we've got carbon-carbon single and carbon-hydrogen. So let's go over to the table. Carbon-carbon single bond, that's 348 kilojoules per mole. Okay. All right, sorry, it's taking me a little while. So that's 348 kilojoules. All right, and we'll so if we have 2 of those, that's 348. Let's go down here and start to fill in our table. Carbon single bond. We have we have 2 moles of those. So that's 2. Now, why am I saying 2 moles? Well, because in the balanced chemical equation, we know the equation says there's 1 mole of propane that reacts with the rest of this stuff. But every mole of propane contains 2 moles of carbon-carbon single bonds. So that's why the 2 is there, and that's why I'm labeling this 2 moles. And the energy per mole is 348 kilojoules. All right. Then we have carbon-hydrogen single bonds. And we have 8 moles of those. And those are worth 413, right? So if you go over to your table, carbon-hydrogen, 413. So there we go. 413. All right, and then what else? Then we just have the oxygen-oxygen double bond. and we have 5 of those. And if you look up on the table, each oxygen-oxygen double bond is 495. Okay, so now what you have to do is you have to multiply the energy per mole by the number of moles. Okay, so when you take 2 times 348, you'll get 696. When you take 8 times 413, you should get 3,304. And when you multiply 5 by 495, you should get 2,475. All right, and when you take the grand total on the bond breaking side, you should come up with positive 6,475 kilojoules. Okay, now if you do the same thing on this side, all right, what you should end up with is, you know that you've got 6 carbon-oxygen double bonds, and those guys are worth 799 kilojoules per mole. Now notice I'm using a minus sign here because these bonds are being formed. That's an exothermic process, and so you have a negative sign associated with that process. Whereas these were all bond breaking, and that's endothermic, so that's positive. And then over here we have oxygen, hydrogen, single bonds. We have 8 of those, and those are worth, if it's bond formation, it's negative 463 per mole. And when you take the grand total on that side, you should come up with negative 3704. Okay. Oh, I'm sorry. That was the grand total of the oxygen hydrogen. Sorry about that. The actual grand total is negative 8,498. Okay. Sorry, I don't know what happened to the 8 there. Negative 8,498. All right. Now, to calculate, to estimate the overall energy of reaction, okay, so that's what we're trying to do. For this reaction, we're trying to come up with an estimated, EST, estimated energy of reaction. And the way we did it is we tallied up all the different types of bonds, how many of each one we have, and then we remembered that any bond that's being broken is going to be a positive contribution because it's endothermic, and any bond that's being formed is a negative contribution. That is, it's contributing towards stability. And so then when we come up with the overall estimated enthalpy of reaction, we simply add the bond breaking energy to the bond formation energy, and we're paying attention to the signs. And I think you can see that overall this is a negative enthalpy, and what you get is 2,223, and that's kilojoules per mole. Now, as I keep saying, that is an estimate. The experimentally determined heat of combustion for propane is 2,220 kilojoules per mole. All right, and so the estimate, we're off by about 9%, but that's okay. That's okay. That's pretty darn good. And there, because this is an estimate, we're making some approximations, which we don't need to get into in a first-year chemistry course, but it's a really good way of understanding why some reactions are more, produce more energy than others. Okay, so that should help you now get started. So the first problem on your problem set has to do with methane. So now that we've gone through propane combustion, this reaction should seem like a piece of cake. All right, you should be able to do all 3 on this problem set. Okay, so good luck.